All right, we're about to dive into a book that's over 2,300 years old. Sounds ancient, right? But what's incredible is that it's the invisible blueprint for almost everything in our modern world. I'm talking from the skyscrapers in our cities all the way to the code running on your phone right this second. So let me just kick this off with a question for you. What do you think is the single most successful, most influential, and longest running textbook in all of human history? Well, the answer is a collection of 13 books, known simply as Euclid's Elements. And for more than 2,000 years, this one work has been the absolute gold standard for how to think logically. But to really get why this book had such a massive, seismic impact, we gotta go back in time. Back to the place where it all started, the intellectual heartbeat of the ancient world. It was written way back, around 300 BCE, in Alexandria, by this kind of mysterious mathematician named Euclid. And here's the crucial part. The Elements wasn't just a list of facts. In fact, many of the theorems weren't even his own discoveries. Euclid's true genius wasn't about what he presented, but how he presented it. You see, he didn't just collect knowledge, he created a system. And that system, that is the whole key. Euclid didn't just give us a bunch of answers. He gave us a method, a blueprint, for proving that those answers were undeniably universally true. It was a blueprint for logic itself. I mean, just think about what math was like before him. It was pretty much a jumble of useful tricks and things people noticed worked. The Egyptians were brilliant at building pyramids, but they couldn't formally prove why their geometry worked every single time in every case. Euclid was the one who came in and brought this beautiful, rigorous order to all that chaos. His system kicks off with the absolute basics, definitions. Before you can prove anything, everybody has to agree on what the words actually mean. So he gives these super precise definitions for things like a point, a line, a circle. Take parallel lines. He says they're lines that, even if you stretch them out to infinity, will never ever meet. It's crystal clear. There's no wiggle room. Okay, next up, the postulates. Now you can think of these as the fundamental rules of the game. They're a tiny set of statements that are so obviously true, so self-evident, that you just accept them without needing a proof. For example, the idea that you can draw a straight line between any 2 points. I mean, of course you can. This is the solid, unshakable bedrock for the whole system. And finally, with our definitions and postulates locked in, we get to the main event, the propositions. These are the theorems, the bigger, more complex truths he wants to prove. And every single one is built, step by logical step, using only those shared definitions and self-evident postulates. Nothing is taken on faith. So this is the method in a nutshell. You start with a solid foundation of stuff everyone agrees on. Then you build on it using pure, rigorous, step-by-step logic, and you arrive at a proof that is just as solid as the foundation it's sitting on. It's like building a logical skyscraper, brick by perfect brick. So, okay, how does this actually work in practice? Let's see it in action. We're going to walk through the very first proposition from Book 1, just like a student would have done more than 2,000 years ago. The goal sounds simple, right? Make a triangle where all 3 sides are exactly the same length, and all you have to start with is one straight line. But here's the catch. You can only use the tools we've been given, our definitions and postulates. No rulers for measuring, no protractors, just pure, undeniable logic. Okay, step 1. We start with our line segment. Let's call the endpoints A and B. This is our starting block allowed by postulate 1, which just says we can draw a straight line between any 2 points. Easy enough. Now we bring in another one of our tools, postulate 3. This one lets us draw a circle with any center and any radius. So let's plant our center on point A, stretch the radius out to the length of our line AB, and boom, we draw our first circle. Now we're just going to do the exact same thing again, use postulate 3, but this time we slide over to the other end. We'll set our center at point B, use the same radius, the length of BA, and draw a second circle. You can probably see where this is going. So these 2 circles cross each other at a new point up top. We'll call that point C. Now we just use postulate 1 again to draw a line from A to C, and another from B to C. And there it is, our triangle. But the big question, is it equilateral? Well, think about it. AC is a radius of that first circle, so it has to be the same length as AB. And BC is a radius of the second circle, so it also has to be the same length as AB. So all 3 sides must be equal. And that, right there, perfectly shows the power of this method. We haven't just drawn a triangle that looks about right. We have proven with absolute logical certainty that it's equilateral, as Euclid himself would say at the end of a proof, which is the very thing it was required to do. It's just so elegant, undeniable, perfect. But here's the thing. If you think The Elements is just a book about triangles and circles, you're totally missing the bigger picture. Because the sheer scope of these 13 books is, frankly, breathtaking. I mean, across these books, he dives deep into the properties of circles. He develops this brilliant theory of proportion that could finally handle irrational numbers, which was a huge headache for the Greeks. He gets into number theory, exploring prime numbers, and it all culminates in constructing the 5 perfect Platonic solids. This is an entire universe of math, all built from that same simple logical foundation. So why on earth does a 2,300-year-old math book still matter to us today? Well, because its real subject wasn't just shapes. Its real subject was truth itself. You see, the most important thing to take away from Euclid isn't any one specific proof about geometry, it's the method itself. This idea of starting with shared assumptions, or axioms, and building a case, brick by logical brick. This became the blueprint for all rational thought that followed. And once you see this pattern, you start seeing it absolutely everywhere. The scientific method? That's basically Euclidean. You start with a hypothesis, your axiom, and you test it with logical steps. Computer programming is just pure applied Euclidean logic, following strict rules step by step to get a result. And think about a legal argument, a philosophical debate, or even just a good persuasive essay. They all rely on this ancient blueprint, building a solid conclusion from a firm shared foundation. And that is the incredible, enduring power of Euclid's Elements. It didn't just teach us what to think about shapes, it taught us how to think. Full stop. It showed all of us that from just a handful of simple, accepted truths, we could use the power of pure logic to build entire universes of certainty. Which kind of leaves us with one last question for you. What can we build with it?